It is, in fact, very much a treat for me to be here and give a seminar in the I for Energy seminar series. So I want to thank Carl and Therese for inviting me. I must say I've been a fan of the seminar series since I was a Ph.D. student at Michigan, watching these videos on YouTube and trying to keep track of, ground zero of what's happening in the space of energy. So with that, today I'm going to talk to you about electrified vehicles, and in particular I'll talk about energy management. I'm going to describe some solutions that exist out there, and I'm also hopefully going to motivate some key opportunities that exist within this space. Now, although this specific talk is focusing on electrified transportation, so you see that vehicle and bus down there, my interests expand beyond that, all the way into the grid, integration of renewables, and the built environment. But today I'll focus on transportation in particular. So I don't have to motivate this audience on why we want to think about energy, but I'll provide a particular framing that's interesting. Namely, here's some data on the world energy consumption over the past few centuries, and when I first saw this plot, I thought it was rather sobering to see this exponential rise in our energy consumption. So, extremely interesting. Point here being that we need to think a little bit more carefully about how we consume energy. And in this talk, I'll focus on transportation, which roughly accounts for about a third of energy needs. Now, focusing a little bit more on electrified vehicles, here's a plot of electrified vehicle sales in the United States over the past couple years. And what you can see is electrified vehicles are coming. You see them on the road. It's funny because Berkeley, I notice way more Priuses on the road here than pretty much any other city I've ever been to in the world. So some data. In calendar year 2012, about 500,000 electric drive vehicles were sold. About 10% of those were plug-in electric vehicles. And I'll define the difference between plug-in electric vehicles and just electric drive vehicles in a moment. But this number is increasing. They are coming. Now, outside of the U.S., here's some data that is projecting the transportation market in China by 2050. So I pulled this plot from a study at Lawrence Berkeley Lab up on the hill where they have these models that are predicting under a conventional integration scenario and a more aggressive integration scenario what the distribution of electric vehicles will be in 2050. And what you want to focus here is on this light purplish color. So in 2050, about 30% more or less of light-duty vehicles will be electrified. And under an aggressive scenario, it could be as much as 70%. Another interesting statistic that I learned on a recent visit to China is actually, for mobility, electric vehicles in China already outsell conventional vehicles. And the reason for that is because electrified scooters are the most popular form of transportation, most of which are electric powered. So in countries outside the U.S., this is crucially important. So there's two sides of my research program. One side deals with electrified transportation. The other side is smart grids. And this talk, I'll talk about batteries and energy management. But let me take a moment here to define the different types of electric drive vehicles. So there's basically three types. Some of you may be familiar, some of you not so much. But just to, for an introduction, let me first define these three categories. So the first of which is hybrid electric vehicles. Hybrid electric vehicles, their energy ultimately comes from the gas pump. The internal combustion engine is the primary energy source. They have a battery, but it serves as a buffer. Okay, so it's only a buffer for regenerative braking, and it serves the purpose of allowing the internal combustion engine to operate in its sweet spot. So Toyota Priuses that you see all over Berkeley, for example, are of this type. The next more advanced form of electrification is plug-in hybrid electric vehicles. So these vehicles have both internal combustion engines and batteries. And both of these are depletable stores. You can deplete the gas tank and you can deplete the battery. And respectively, you can refuel them at the pump or when you plug in. So the Chevy Volt is an example of this. Then the full form of vehicle electrification is this all-electric vehicle. So this has no internal combustion engine. It's a battery only, and you need to plug in to quote-unquote refuel. So this is the Nissan Leaf and Tesla Model S. Now, with each of these different levels of electrification comes different levels of problems, technical problems that we need to think carefully about. One of which extends across all of them, is the battery. The battery is the key technology here. Okay? It is also the most expensive component in these vehicles, so I'm going to focus on that. The other issue is energy management. So it's the question of, when I push the gas pedal in, for example, a plug-in hybrid electric vehicle, how does it know when to use battery and when to use engine? So with that, let me outline the rest of the talk. We're going to start out sort of at a micro view, talking about batteries and the problem of estimating state of charge and state of health. I'll define that more clearly in a moment. Then we'll zoom out a little bit and talk about energy management and plug-in hybrid electric vehicles, and zoom out just a little bit further and see how that can integrate with the transportation infrastructure using velocity forecasting. And, of course, this is work done with many collaborators, of which I'll highlight as I get to each section. So let's start out with electrochemical-based battery state of charge and state of health estimation. So this is collaborative work with Nolan Chaturvedi at Bosch Research and Technology Center in Palo Alto and Miroslav Krstić at UC San Diego. So here's the battery problem encapsulated in one slide. The needs are, we need them to be cheap, we need them to have high energy and power, we would like them to charge quickly and last a long time. But the reality today is they're expensive and far and away conservatively designed and operated, and they die quicker than we'd like. And this conservative design and operation is what I'm really going to harp on in this section of the talk. So some motivating facts here. So in electrified transportation, in 2010, batteries roughly cost about $1,000 per kilowatt hour. Today, or in 2012, we've made significant advancements. We've cut that in a little over half, but we still have a ways to go to become economically on parity with internal combustion engines, setting aside all incentives that come from the government. Now, another interesting motivating fact is in electric vehicles, it turns out that often only 50 to 80% of the available capacity in the battery is being used. It's being used conservatively because people don't really understand what are the limits of its operation. This is an issue because it is directly related to range anxiety, which is the key inhibitor of electrified transportation. And then there's the issue of fast charging, but there's clearly a trade-off in the lifetime of the battery. Okay, so we're going to carefully look at this. Now, there's two solutions to this, right? There's, as I like to say, you can either design better batteries or make current batteries better. So what I mean by that is designing better batteries is really a material science or chemistry question of what is the next great material out there. Now, as a control theorist, I'm going to focus here on making current batteries better. That is, how do we really squeeze out as much performance and lifetime out of these systems using models, estimation, and control theory. So let me give you an overview of the different ways people think about modeling batteries in electrified transportation, or even in grid-scale energy storage, or even mobile phones. So the first category of models are the so-called equivalent circuit models. And the idea is super simple, super simple. You can model the voltage and current behavior, so this is the input-output behavior of the battery, by writing an equivalent type of circuit. So here you have a voltage source in series with a resistor, and clearly a battery is physically not this, but you can mimic the behavior roughly with this type of model. And you can make it progressively more complex by adding more circuit components to capture more and more of the dynamics. So these models are nice because they're simple, they're intuitive, in heat transfer, of course in electric circuit design, in many different areas. We like to look at resistors, capacitors, voltage sources as a way to try to understand the fundamental behavior. Now, recall that my original motivation here was to extract as much performance as possible out of these batteries. So to that end, these models don't cut it. Reason being because if I really want to understand the physical limits of operation that have to do with the electrochemistry that's happening inside the battery, these models don't predict that type of behavior. Which leads us towards the second category of models, these so-called electrochemical models. And here's a schematic shown here. So let me explain at a high level how batteries work. So you can take a battery cell, pretend this is a battery cell in a cylindrical shape. You can actually pop off the end caps, okay? And you can unroll it. It turns out to be a jelly roll of multiple layers, okay? Now, 3 of those layers are the anode, separator, and cathode. And the key property of batteries is that the materials for the anode and cathode are selected such that there's a release of Gibbs free energy when lithium ions move from the anode to the cathode. That's the key property, okay? So when a battery discharges, what happens is these lithium ions exist within the solid matrix of particles. And as the battery discharges, the lithium diffuses from the interior of these particles to the surface, undergoes an electrochemical reaction where lithium splits into a positive lithium ion and to an electron. Now this positive lithium ion diffuses and migrates through the electrolyte in the anode, through the separator, and to the cathode. Now because the separator is insulating, it's a separator in the electric sense, the electron will flow through this external circuit, which will power your device, like your electric vehicle, and it'll meet back up with this positive lithium ion on the cathode side to satisfy conservation of charge. It then undergoes the exact opposite electrochemical reaction where this lithium will then diffuse into the interior of the solid phase of the cathode material. Okay? So roughly at a high level, that's how batteries work. Now, this type of behavior and more is crucially important because if I want to understand how to maximize performance of batteries, I want to understand this fundamental behavior. The problem is I can't measure that, right? We can't measure that. Typically, all we can measure is voltage and current. So one way to think about this, and this is an analogy I typically use, is maximizing performance of batteries is like the person at the front door of this seminar who has the doors closed, and then at noon they open the doors and allow a flow of people to come in. Now the goal of that person is to fill this theater as full as possible, as fast as possible. Now like batteries, in this game, that person cannot see inside the theater. Okay? So as people migrate through the aisles here and into the rows, there may be traffic jams, right? And in fact, there may be broken chairs, which is somewhat analogous to what happens as lithium ions flow through the electrolyte and the solid phase material. Okay? But the person can't see that. They cannot see that. But their goal is to fill it up as fast as possible, as full as possible. This is an analog to what we're doing. So clearly, we need some sort of model for how people flow into theaters, how lithium ions flow within batteries. Okay? So why is that? So traditionally, the way batteries are operated is the limits of operation are constrained to what we can measure, namely the voltage and the current here. Okay? Now, this fundamentally new paradigm that we're exploring here is limiting the internal variables that I cannot measure, but those that I could estimate from models. Things like overpotential or surface concentrations. And what happens is when you map this operating region into this space, is that you can see immediately how conservative we currently are with batteries. Okay? So we're going to extend from this red region the limits of operation to the green. Okay, so that sounds great. Sounds like a very clear path we want to take. Why is it difficult? The reason it's difficult is because the mathematical equations which model this electrochemistry type behavior are complex. So I'm showing you these equations not so that you understand the details, but to get to the point across that it's complex. Namely, and the complexity is what I find interesting as a control theorist. Namely, we have coupled nonlinear partial differential equations. So you have, for example, the lithium concentration in the solid phase. This is diffusion in spherical coordinates. lithium concentration in the electrolyte phase is linear diffusion. You have these ordinary differential equations in space. You have these nonlinear algebraic constraint. So mathematically it's complex. And the control theory that we learn in introductory control classes here at UC Berkeley doesn't cut it. So this really is an opportunity to develop an advanced control theory for partial differential equations. So that's my technical interest. Let me show you just a video animation of this battery behavior. So what I'm showing you here is, on the bottom, first focus here, this is current and voltage. Current is in blue and voltage is in green. And what we're doing here is pulse charging of this battery. Okay? And these three plots correspond to concentration of lithium in the battery. In the middle here, this is the concentration in the electrolyte phase as it extends across these three layers of the battery. And on the top, this is the concentration of lithium in the solid phase, in the anode and the cathode. And as we move from the bottom up, the bottom is the surface of these particles, and on the top represents the center of these particles. Okay? So I'm going to play this video, and I want you to focus on the dynamics as they evolve both in space and time. So let me remind you again, all we have access to are these waveforms underneath. But if I really want to extract as much as possible out of batteries, I need to understand everything that's happening up here and more. So clearly not an easy problem. Okay, so I won't go through the technical results, but sort of go straight to the results. So we've done some work on extending PDE estimation theory, which allows us to estimate the concentration of lithium, which is essentially our measure of state of charge, the energy level of the battery. And then we make this adaptive by saying there are parameters that I don't know in those models that are correlated to the state of health of batteries. So this leads to adaptive estimation techniques, which are represented by this red block and green block, and you can refer to this paper for details. And these spit out parameters that ultimately correspond to the energy capacity of the battery and the power capacity of the battery. So now and here's some simulation results. So what I'm showing here on top is we're exciting the battery with a charge and discharge cycle that's similar to what a battery undergoes in a plug-in hybrid electric vehicle. And in blue is the true state of charge up here, and in red is what you think the true state of charge might be. So your vehicle initially, say it's totally initialized incorrectly, your vehicle tells you it has 30% charge, when in reality it's 60%. So over the course of this drive cycle, it's going to recursively identify the true state of charge and eventually converge to the true value. Simultaneously, it's on this side, it's identifying parameters related to its state of health. And the key property here you want to show is that they don't go off to infinity, but they're bounded somewhere close to the true values of normalized to 1 here. So now that we have some idea of how to estimate these electrochemical states, the next question to ask ourselves is, given accurate state estimates, can we govern the electric current such that safe operating constraints are satisfied? So moving from this paradigm on the left to the right. So far what I've shown you is, some ways in which we can identify what these electrochemical states are by only measuring voltage and current. So how do we extend this operating range? So I said that we want to constrain these important internal electrochemical variables, and I'm showing some of those here. So these are related to the concentration of lithium, temperature. I'm going to show some examples where we focus on the side reaction over potential, which is one of these internal variables. Why is this variable important? Well, when this variable becomes negative, that corresponds to lithium plating. And we've all heard, perhaps at a high level, of lithium plating and this dendrite formation. This is the issue when lithium-ion batteries can catch fire. We've all seen these videos on YouTube. I think Boeing recently has probably been thinking pretty carefully about this particular degradation mechanism. So we do not want this to become negative because bad things can happen. So how do we enforce that explicitly? So what I'm going to show you, and I'm going to show you some equations but explain how it works at a high level, is we're going to use a technique in control theory called a reference governor. Okay? And the idea is follows. So this is my physical battery cell. And let's suppose that through my estimation algorithm, I can perfectly estimate these electrochemical states, represented by X and Z. Now, on the outside, the system is telling me I want some requested current IR. Okay? What this modified reference governor does is it's like a speed governor in your car. Okay? What it does is it takes this requested current and it takes these estimated states and it will attenuate the current if it violates safe operating constraints. Namely, what it does is you give it IR and then in the next time step it will apply I scaled by this parameter beta, which is between 0 and 1. And you want beta to be as close as 1 as possible such that safe operating constraints are satisfied. So how do you do that? What this says is that you'll take the current state estimates, you'll initialize your electrochemical model, and you run it forward over some time horizon. So suppose that the supervisory control system says, I want 20 amps from my battery. It'll then simulate the battery with 20 amps. And if safe operating constraints, defined on the previous slide, are violated, it'll then reduce 20 amps to 10 amps. Then it'll resimulate the model. If no safe operating constraints are violated, it can increase it to 15 amps. And then it'll iteratively go through this optimization process to determine what is the maximum safe current such that I satisfy these constraints. So you get pictures like these. So here's a pulse charging of batteries, of a battery cell on this slide. And here's the side reaction over potential, which over time could become negative, which could cause lithium plating. So if you don't estimate this variable, you have no way to identify if this is happening until something bad happens. So what this algorithm does is it'll attenuate the current here such that you could safely ride against this constraint. So this is about safety. Okay? Now another interesting application is in charging. So what I'm going to show you is charging batteries using a traditional method, this constant current, constant voltage scheme, and this more advanced method, this modified reference governor. So constant current, constant voltage is exactly what it sounds like. This is how batteries in your phone, in your laptop, and to some degree in your plug-in electric vehicle charge. Okay? What it does is applies constant current in the first phase until the voltage reaches some upper limit, for example, 4.2 volts. Once you hit 4.2 volts at this critical point, it'll then apply constant voltage, and the current then attenuates down to 0. Now, this 4.2 volts that's set by the manufacturer is actually a conservative selection, because what the manufacturer is worried about is that you can cause constraints like the side reaction over potential to become negative. But because you can't measure that, that's inherently conservative. So there's some additional opportunity here that you could take advantage of if you understood more. Okay? So that is exactly what this modified reference governor is doing, is it's allowing you to overcharge your battery or safely go over the manufacturer's specified limit because you're explicitly enforcing safe operating constraints. So you can exceed this limit, eliminate this conservatism, and interestingly, you can get 5% more charge capacity. And in this particular case, a 20% reduction in the 0 to 95 charge time. So that's pretty cool. Let me show you another really interesting example. So in black, this application was motivated by smartphones. So in black, you have how smartphones charge. They use 0.7 C, constant current, constant voltage. Now, with these more advanced techniques, you could actually charge your cell phone faster and get a 0 to 20% or 0 to 50% charge time significantly faster than what you otherwise could do. And here's some numbers here. So the traditional way is in red, this 0.7 C, and this electrochemical-based control strategy is these two columns on the right. So what you can see here is that we can cut the charge time here by almost a factor of 4, and in this case 0 to 50, and by a little more than a factor of 2. Okay, so that's pretty interesting. Okay, the next two sections of my talk are significantly shorter, but I want to zoom out a little bit and now think about plug-in hybrid electric vehicles and how this plays a role in their energy management. So this is collaborative work with my advisors, Hossam Fathi, who's now at Penn State but was at Michigan, Duncan Calloway, who was also at Michigan, I was working with, and is now here, and Jeff Stein, who is still a professor at Michigan. So the problem statement here is that suppose we have a plug-in hybrid electric vehicle, okay? The question is, how do we design a supervisory control algorithm such that when I hit the gas pedal, how does it determine how much power goes to the internal combustion engine and how much power goes to the battery? And we want to do that in some optimal sense, okay? And the unique thing that I'm going to talk about in the next couple slides is clearly you want to do that in a way that you minimize the cost that you pay for fuel at the gas pump and the cost you pay for electricity when you plug in, but you would also like to do it in a way where it doesn't degrade your battery too fast. So the previous section was about how do we just monitor when batteries are aging. This section is about how do we actively do something about mitigating how quickly batteries degrade in plug-in hybrid electric vehicles. So in this particular study, we focus on what's known as a power split PHEV model. So the details I won't go through, but this is representative of what's in the Toyota Prius. And what you have here is this internal combustion engine, this battery pack. You have two motors. And you're interested in fuel consumption costs, grid electricity consumption costs, and also the battery's state of health. And what you want to design is this block up here, which takes in these state variables and these control inputs. Now, I'll also mention that how you drive the car plays a significant role in how you divide power between the engine and the battery. And that's encapsulated in this block here where drive cycles are modeled with a Markov chain. I won't go into detail on that, but we'll talk about that a little bit in the next section. So the control optimization problem is how do we minimize energy consumption and battery aging? So we can formulate this as an optimization problem. So in my CE 191 class, which is essentially about optimization, this is a typical problem format that these upper division undergraduates see. So what you have is some cost functional that you're trying to minimize here. So in this case, you're trying to minimize the expectation of these per time step cost functions C, where C is the convex sum of energy cost and battery health here. Okay? And this is subject to constraints on the dynamics of the PHEV. And what these two set constraints represent is just safe operating constraints of your vehicle and your actuators here. So the goal is to find this control law G, which maps these states to the control inputs such that you minimize energy consumption costs and battery health degradation. Now let me point out alpha. This is an important parameter here because we're trying to optimize two things. Okay? Now alpha can vary between 0 and 1, and that allows us to trade off between energy and health. Namely, when alpha is 1, all we care about is energy, and this term on the right goes to 0. And when alpha equals 0, then all we would care about is health, and the energy term goes to 0. Okay, so we can look at the trade-off between these two objectives. All right, and those are the forms for each of those objectives. Okay, so this was essentially my dissertation topic. 5 years later, you get this. Okay, so what this is the Pareto set of optimal solutions, and it's a bit of a dense slide, but let me break it down for you. So what you have is the two objectives that you're interested in. Namely, you have energy economy on the vertical axis. So this is how far you can drive in kilometers per US dollar spent on fuel or electricity. And on the horizontal axis, you have a particular metric for how batteries age, namely the salt electrolyte interface film growth. This is one of the main contributors to how batteries age. And each of these stars represents some optimal solution. Okay? Actually, to be more correct, it doesn't represent one optimal solution, but the mean of a distribution of optimal solutions. Because each of these solutions is specific to a particular driving cycle. Okay? So the stars represent the mean of the performance, and these ellipses are the 25 to 75% quantile range. So you can see the distribution here. Okay? So clearly what you want is high energy economy and low film growth. So what you want to move to is the upper left. Okay? But there's this clear trade-off between energy consumption cost and battery health that is being traded off here. Okay? So individuals might want to make the decision of how much am I going to pay at the gas pump or in my electric utility bill versus how quickly do I want to degrade my battery. So let's look specifically at a couple solutions here, namely the two extremes and one mixed solution. So here's what happens in your vehicle when you care about the two extreme solutions or the mixed solution. So if you care only about energy, what it's going to do is blend fuel and battery energy. And it turns out that the optimal thing to do is to blend fuel and battery energy such that exactly when you reach the end of your trip is when you reach the minimal SOC. That is the optimal thing to do. So think about this for a sec. So if you go and buy a PHEV out there and they tout how much the all-electric range is, what I'm telling you is if you're just trying to get the most electric range as possible, that is not optimal. Okay? Assuming that your trip length is longer than the potential all-electric range. So if you depleted the battery completely and then blended, that's worse for energy consumption cost. First important conclusion. Now, it turns out that if all you care about is the health of the battery, represented by this solid electrolyte interface layer, it turns out the optimal thing to do is to deplete the battery as quickly as possible. So that's a tad surprising. And it turns out that these degradation mechanisms, this one in particular, happens faster at high SOC than low SOC. So this also has an impact on how you want to charge electric vehicles. Namely, if this degradation mechanism is dominant, then what you want to do is to keep your electric vehicle battery discharged for as long as possible, only charge it when you need it for only as much as you need, drive it, and then let it sit at low charge. Okay? This is also interesting because the way a lot of people use their laptops and the way some people use their cell phones is not like this. Right? And then, of course, when you care about both, it's going to be some mix in between. Okay, so that's all I want to say about energy management. Let's go to the velocity forecasting problem. So, now, an interesting thing about energy management in hybrid electric vehicles and plug-in hybrid electric vehicles is that if we know the driving behavior of individuals exactly, a priori, then we can achieve provably optimal economy. If we had somehow clairvoyance of exactly what your trip was, what the traffic was, we could do this in an optimal way. But the reality is that perfect drive cycle information is never known a priori. Okay? So what can we do in terms of trying to better forecast what the drive cycle is, what the velocity behavior is? So let me introduce a control theoretic tool first. Namely this model predictive control strategy. So this is going to be very useful for this particular problem. Here's what model predictive control does. What model predictive control does is it'll optimize, for example, your energy economy in your plug-in hybrid electric vehicle by simulating a model forward in time over some short finite horizon forward in time, and it'll use some forecast for what your velocity is. Over this control horizon, it'll find the optimal trajectory and then implement the first time step, implement the first control. Then, as you drive one more time step, it'll then restart this whole process. It'll simulate over the same time horizon, forward in time, optimize the control trajectory, and then implement the first control. And it'll continuously do this in this receding horizon format. So the key here, though, is we want to somehow forecast what velocity would be over that short time horizon. Okay? So the punchline is better velocity forecasts will produce better or lower fuel consumption and emissions. Okay, so the full picture is going to be this. This is similar to the one we saw in the previous section where you have your hybrid electric vehicle, some low-level controllers, and then the work that was done, for example, in the previous section, or you could use a model predictive control framework, could occur here. The significant block is this one, this horizon velocity predictor or forecaster. Okay? So that's what we want to understand better. So it's interesting because in this literature, often researchers have kind of thrown their hands up in the air and say, well, we don't have clairvoyance. We don't know where people are going, and this is a hard problem. So, but there's a few ways that people try to predict these velocity. And here, there were three classes of models that were studied. This generalized exponential varying approach, Markov change, which is what was used in the previous section, and artificial neural networks. So let me explain each of these briefly. So this generalized exponentially varying, the idea is simple. It just says that your velocity at each time step changes exponentially. It either increases exponentially or decreases exponentially. Now clearly that's not real or accurate, but it turns out that can often do well for supervisory control. The next idea is Markov chains. So this is a statistical framework which says, given my current acceleration and given my current velocity, there's some probability of transitioning to different levels of acceleration in the next time step. So this is a statistical framework. And you can do that in a one-stage format or a multi-stage format. Now the next class of forecasters that was studied here was artificial neural networks. So here, the artificial neural networks at a high level is essentially a glorified nonlinear curve fitting. So here you can define the inputs here to be velocity in the previous time steps, and the outputs of the neural network will be the forecasted velocity in future time steps. And different classes of neural networks were studied here. So, Chao Sun, a visiting student with me, studied these three classes of forecasters, and here are the results. So ignore velocity, RMSE, and simulation time just for the moment. Let me explain what these different methods are. So deterministic dynamic programming is the absolute best you could do if you knew exactly a priori your drive cycle. You cannot do better than 335 grams of fuel. Deterministic MPC is the best you can do if you could forecast perfectly the drive cycle over some receding horizon. Okay? So in that receding horizon format, that's the best you can do. Now, all these other these other methods come from each of these classes and are the best from each class of forecasters. And it's interesting because it turns out that this artificial neural network turns out to do the best, and we're going to talk about why in a moment here. So here's that same table of data, but shown graphically. I think this is easier to look at. So this is the increase of fuel consumption as a percentage on the vertical axis on top. So on the bottom, you have the different techniques. So 0 is, deterministic dynamic programming. You know your drive cycle globally a priori. Deterministic MPC is the best you can do in the receding horizon format. And generally, it turns out that this artificial neural network approach seems to do better. Okay? And here you can see what the battery SOC would be when using this model predictive control technique for these various classes. Okay? Now, it's kind of interesting because we don't just want to see what's best, but we want to try to understand why. Fundamentally, why are neural networks doing better? And I have to be honest, before when it was suggested to look at this class of models, artificial neural networks, I was very skeptical. In the control theory literature, I think generally people, they have a negative connotation towards neural networks that can sometimes be perceived as black magic. But in this case, it turns out to capture some structure that the others cannot, which is interesting. So what I'm showing here is the real velocity profiles in blue, okay? And each of these are the various different forecasting methods, okay, over some horizon forward in time. So I jokingly call these the hairy velocity profiles. So what you can see here is on the top, this is the exponentially varying forecasting. And what you can see is clearly it doesn't do very well in capturing the true velocity behavior, but it's decent for supervisory control. When you use the Markov chain framework, either a one-stage or a multi-stage, what you essentially get is a random walk across each, for each time step. Okay? And when you add multiple stages here, an interesting thing that happens is when you add multiple stages, it essentially averages the effect of what your future acceleration might be. That is, on average, or in a statistical sense, it is most likely that you will maintain the same acceleration in the next time step as your current time step, on average, which is why you have these trajectories that are roughly tangent to the velocity profile here. So clearly that's not perfectly accurate. So here you see these neural networks, and what's interesting here is that they seem to capture some more structure. Namely, there's clearly a velocity limit, right, when you're driving, and there's some behavior that when you go on the highway, you will likely maintain that velocity or perhaps tail off. And these artificial neural networks, because of their nonlinear characteristic, are able to capture this structure. So this is pretty interesting. Okay, so let me talk about upcoming work, what's coming soon and what some future opportunities might be. So next door in Davis Hall, we're building a facility to do battery-in-the-loop hardware testing. And what we're excited about at the moment is fast charging. So taking those algorithms that you saw in section 1 and being able to experimentally verify if we can charge batteries faster, perhaps by a factor of 2 or 3, for minimal change in the ultimate cycle life of the battery. So, and this is motivated also in mobile communications. When you look at the worldwide 2012 statistics, 6.7 billion subscription accounts, 5.2 billion handsets in use, 1.7 billion mobile phones sold worldwide, of which about 1 billion are smartphones. So, broader impacts are certainly there. The other thing we're interested in is, researchers in the past I've noticed have thrown their hands up in the air and say, I have no idea what the velocity might be for a particular driver. But now arriving in the civil engineering department and talking with a lot of the researchers here, it's become immediately clear that we, in fact, do know a lot about the driving behavior. In fact, you can in real time get data, it's right on Google Maps, you can get data on what velocity profiles are over the traffic system in the Bay Area here. So this can feed into individual energy management. Namely, if you tell your Prius, for example, here in Berkeley, I'm going to go to SFO to pick somebody up, what we're now starting to look at is a system where it can connect to the internet. It can basically download from the PEMS database or other databases what the real-time traffic information is, and then in real time in this model predictive control framework, optimize what the energy management is for that particular trip. It all just happens automatically. The infrastructure is there. We just need to connect it. All you have to do is say where you're going. And there's also interest in connecting, electrified transportation here with smart homes. I took this picture when I was walking my dog in North Berkeley. There's this home where this guy has this Model S sitting in his driveway, and he has solar panels on the roof, and he's really creating a smart home for himself. And I asked him, what is it like, installing these solar panels? How do you like your Model S? Smart homes are happening. Berkeley is definitely ground zero for things like this. And there's this question of how do we connect these systems so that your vehicle can interact with your home, it could interact with commercial buildings, and potentially the city infrastructure in total. So before I close, I'm going to make a pitch here for classes that are being taught next semester. So for the students in the audience, sign up for these classes. So at the undergrad level, there's this class on design of cyber-physical systems, CE 186. So this essentially is a senior design project-based course where students will get these electric scooters, which will be sort of a proxy for an electric vehicle fleet. They'll then, work on being able to measure current and voltage. They'll use equivalent circuit models to estimate battery state of charge. They'll then send that data through the internet into a database where then we can see how these students are riding around the UC Berkeley campus as they're wearing their helmets that say CE186 on the side. So it'll be a lot of fun. And then for me at the graduate level, I'm teaching a class on energy systems and control, which is motivated by studying energy systems and various infrastructures, transportation, and the electric grid. And we use that application base to study specific control theoretic tools that have become very useful and applicable in this space. So I close with this picture. So I said it's quite a treat to be here. As Therese mentioned, I was an undergrad. In fact, I was, before I was a professor some 10 years ago, I was in the Cal marching band. So, Berkeley runs through my blood. I definitely bleed blue and gold. So with that, I close, and I'm happy to answer any questions.
So I've got a question, Scott, about using my laptop. You seem to be giving some guidance, but I'm not sure I got the takeaway clear. Should I run it at low charge and not leave it plugged in all the time?
There's some software out there, right? It's a trade-off, right? You want it to last a long time, but then if you want to go to a meeting and run on battery, you want enough charge to last through the meeting. So there's actually software you can buy. And I think there's even some freely available software on the internet which will manage your battery charge. So you can make the selection of regulating the battery charge at, say, 50%, right? And they've collected data that shows you can get your battery to last longer if you indeed do that. Of course, you sacrifice something in your mobility with your laptop, but oftentimes that's worth it.
Great talk. My question for you is going back to the section on predicting battery health and using state of health estimators and things like that. That's a really tricky field, and I commend you for applying your tools to grapple this section. I think that the community hasn't even come to agree what's in the solid electrolyte interface and what the mechanisms are that cause it to form and build up and things like that. So I wonder if you could tell us a little bit more about how you went about modeling the SEI formation.
Yeah, so actually we know that SEI formation is bad. We agree on that, and we agree that we don't want it to grow. Now, its particular formation, I am not concerned with the detail of, what are the products in that particular chemical reaction. So in this model, it's modeled with a one-way Butler-Volmer equation, the Tafel equation. Okay, so this is actually taken from work that has, through a few generations out of John Newman's lab here in chemical engineering at UC Berkeley, out of a Ralph White's lab in the University of Southern California. They've done some work where they have this theoretic model for how the SEI layer might grow. So ultimately it comes down to you do not want the overpotentials on the anode side to become too large. So that's, in this context, we just don't want it to grow fast, and that's all I'm concerned with. But I'm very interested to understand more about what are the key degradation mechanisms. So if you have information on that or some guidance, I'd be more than happy to talk about it.
I'd like to second my colleague Sam's commendations. A great talk. I'm curious to know about the economic implication of your result, where you had the the state of charge versus the dendritic growth curve. Now, if oil prices crash, right now it's a corner solution for a PHEV. You want to use as much electricity as possible because it's a much cheaper fuel.
Right.
Now, I was just wondering if you did sensitivities on that sort of global picture.
Yeah, we did. In fact, a paper I co-wrote with Duncan Calloway, who's now here, studies that sensitivity with respect to battery size and fuel and electricity prices. I'm just going to our particular parameter, which is the parameter used in that sensitivity analysis. So it's beta. This parameter beta encapsulates the cost of, it's the energy price ratio is what I call it. So it's the ratio of price of gas price versus electricity price. Okay? So if something crazy happens and electricity somehow becomes extremely expensive, then you can actually get cases where you will use your plug-in hybrid electric vehicle as an electricity generator, which you can then sell electricity. You will convert fuel into electricity and sell it back to the grid. Now, is that realistic? Is that going to occur? Probably not. But nonetheless, there is this sensitivity analysis, and ultimately what happens is it just affects the rate at which you mix, or how quickly you deplete battery charge here. Check my website. There's a paper on that.
I'd like to also second or third in my colleagues' comments about your talk. It's brilliant. I think I have two questions. One is how robust are your results with respect to battery chemistries? Future battery chemistries are likely to be different. So that's question number one. And then second question is regarding alpha. It seems like from your presentation that alpha is closer to 1 or more realistic. So could you just speak briefly about how you thought about framing the problem in that regard?
Question one about robustness to different battery chemistries. That's a great question. And the short answer is, we don't understand enough about this, right? Because the key of all this is that we understand the electrochemistry and we can parameterize it well. So that kind of assumes some knowledge. So the question is, what if that knowledge is bad, right? So we're beginning to start to think about a structured way to do parameter sensitivity analysis on that large electrochemical model. So that slide you saw with all those partial differential equations. And I have a collaboration with Bosch Research and Technology Center where they have the bandwidth and some former graduates of John Newman who are characterizing these different electrochemical parameters. But the question also is, how do you prioritize which parameters are most important to characterize, right? And another issue, and this is mathematical, but is there linear dependence between parameters? That is, if you perturb two parameters in certain ways, will you not be able to see a perturbation in your voltage on the output because they're linearly dependent? So that's an open question that needs to be solved. And I think nonlinear parameter sensitivity analysis is the answer, at least from my orientation. Your second question was about alpha. What makes sense? I mean, I think this is ultimately up to, the user or the OEM. It's a parameter one can select to determine how they want to optimally make this trade-off. So I think it's just one of those weighting questions of, what do you prioritize one versus the other? Now, some people have asked me, they've said, can't you collapse these two axes? Can't you say that there's some lifetime cost associated with battery degradation, sort of amortize the cost of a battery as it dies over time, and then you could collapse those two, and then you could, in some sense, eliminate this trade-off, right? So it's not a multi-objective optimization. I tend to go away from that because battery costs are evolving so quickly, and I'm not an economist, so one could think about answering that question in that way.
Thank you.
I think we are out of time for today, but I'm sure, can you stay around for a few minutes?
Yeah, I'll stick around.
Okay. Let's thank Scott one last time.
Thank you.